Vale, perfecto. The floor is yours. Bueno, puedes empezar.
Well, good afternoon, everyone. Welcome to our IPARCOS-seminar. Today I'm pleased to introduce Dr. Isabel Rebollido. Isabel obtained her PhD in astrophysics in 2020 from the Universidad Autónoma de Madrid under the supervision of Dr. Eva Villaver and Dr. Benjamin Montesina. Her work focuses on the investigation of exocomets and the circumstellar gas around main sequence stars. She then moved to the Space Telescope Science Institute in Baltimore, where she worked with Dr. Marshall Perry and Dr. Christine Chen on HST and JWST data of the drift disk. In 2023, she returned to Spain and Juan de la Tierra Fellow, joining the Center for Astrobiology to work on imaging and spectroscopic observation of the drift disk. Since January 2024, she has been a research fellow at ESAC, where she continued her research on the drift disk. She's currently part of the JWST Telescope Science Team, the Early Release Science Direct Imaging Team, the HEOPS Science Team, and part of another study analysis group to investigate the exozodiacal light and its impact in future emissions. Today, Isabel will present on the topic a comprehensive view of Beta Pictoris system. So thank you very much, Isabel. The floor is yours.
Thank you, Enrica. Thank you, everyone, for coming, and thank you, Isabel, for inviting me. It is my pleasure to be here. I'm really happy to be a Complutense. And I'm going to talk about a lot of different work, but always on the same system. There's a reason I'm talking about this system. I hope you leave the room thinking, wow, this is really cool. But that's the goal of every speaker, right? So let's see where we get. I'm happy to take any questions if you want, especially for the people that are here. And of course, we'll have some time, I hope, afterwards. Yeah, so why Beta Pic? We'll never know. Ahí está. Okay, that's fine, that's fine. It was just sorry about that. Okay, so why Beta Pic? And you'll see that the introduction is going to take me a while before I actually start talking about the data that I took or the data that I analyzed. So Beta Pic was the first system that was ever imaged, the first planetary system that was ever imaged. This was in 1984. Half or 75% of this room was not born in 1984, including myself. And this was a time in astronomy, like we talk about, like, oh, we're in a golden age of astronomy. We have been in a golden age of astronomy for a few years, actually. And this was when we were starting to look at infrared data. And the first infrared evidence that Beta Pic was actually interesting came from a mission called IRAS that maybe you don't remember, that told us that there was dust around these systems. And so when we heard that there is dust, or astronomers back then heard that there was dust, they were like, okay, let's look into this and let's put something to block the light of the star because it's a very bright star and try to see what's around. That's called the coronagraph. And you're going to hear the word coronagraph a lot in this. It's a very young star. It's 20 million years. It's not a protoplanetary disk. The star is evolved. It's a main sequence star. The spectra is consistent with the main sequence star. And the spectral energy distribution, the photometric data that we get in different wavelengths, is consistent with this star not having a protoplanetary disk. So our main sequence here, planets are formed, and I'll get to that. It's also very close. And that's also another important characteristic to study star, especially like now we have very sophisticated instruments, but 40 years ago, astronomy was harder to do. So it was a very big advantage that the star was very close. And it's very bright in the infrared. That's how we access actually the the planetary disk, the dust that it's here. And I didn't write it here, but if you go to the legend of this image, it's a huge disk. We're talking after the protoplanetary phase, most of the protoplanetary dust and gas is depleted, it has been dispersed from the system. This is what we call a Kuiper belt analog. Now, Kuiper belt is much smaller than this, and I can already tell you that the disk is even bigger when we actually look at different wavelengths. So we're talking about 2,000 astronomical units of planetary system. So, I said it's not a protoplanetary disk, it is a debris disk. And this is the object of my study since basically my PhD. I'm very interested in debris disks because they harbor planets already, but they still have a lot of material that is being processed during this planet formation phase. And it's mostly dust, or at least that's what we see, it's mostly dust. This dust, it has slightly larger particles, slightly smaller particles, and they collide. And those collisions produce more collisions because you have the outcome of the collision moving really fast. And that's what we call collisional cascades. And that generates a lot of dust that we see in these debris disks. They're optically thin, so that means the light is not blocked as it is in protoplanetary disks, so it's actually easy-ish to look through. It is really hard if you have a protoplanetary disk to look what's inside the disk, but it's slightly easier with the debris disk. And this particular one has exocomets, and I think that's one of the things I have the most slides on, because that's what I did my PhD on. This was the first evidence ever of gas in a debris disk. It was not, like this publication does not only have Beta Pic, it also includes Vega, for example, and another star. You know what this is? Yes? Okay. This is the photospheric calcium layer. You see here this is 2 Armstrong bit. So this is really high spectral resolution spectra. And on top of the photospheric calcium line, that it's very rotationally broadened because Beta Pic is an A-type star, so it rotates very fast. We have this very narrow component that it's not from the star because it's not rotationally broadened, it's not rotating with the star. But it's consistent with the radial velocity of the star. It's in the same location as the calcium from the star. So it has to be circumstellar material, and it was attributed and later confirmed as circumstellar gas. So for years, and that was true even when I started my PhD in 2016, we were talking about debris disks don't have gas, while we knew since 1985 that that's not really true. It is way more complicated answer than that. And it not only has this gas that is stable and it's always there, like you took a spectrum out, Beta Pic, and it's gonna show this, but it also has a lot of variable features, like this one, that we attributed or that have been attributed to exocomets. This is the first evidence ever that was reported in a paper as exocomets. By the way, in the paper it doesn't say exocomets because people were not buying it. 1987, we had no planets detected. So there was no way we were going to detect exocomets. So they're called polygon operating bodies for the scientific community's tranquility of mind. So all these variable features, and you can see here that stable feature that we also see here, they happen in different dates, and that it's basically a comet with its nucleus and its tail transiting in front of the star. And the gaseous tail is the one that is producing these small absorptions. Again, these are 2 Armstrongs, so this one here you can imagine, this is in radial velocity. These are really, really, really small features. You need a very stable spectrograph, you need very high resolution, and a big-ish telescope. Yeah, I have to do this here, I think. This is a video of exocomets. Oh, what is the mouse? Oh, it's the other way. Sorry. Yeah. This is a video of exocomets observed in Beta Pic. The black is the median, and the red is exocomets, and you see the dates on the top. And you can see how it varies. Almost every spectra that you take of Beta Pic is going to have variations in it. It's going to have exocomets. It's the most exocomet prolific star that we know. That has not changed in 40 years. I don't know if it's going to show. There was a sort of average, but I think the video didn't say what. So yeah, it has so many exocomets that we even have the opportunity to do statistical studies and to do population studies on this sample. Well, this video was from that. And you can ask, what are exocomets? And I said that they're comets with a solid nucleus with a tail that has gas. At this point, we hadn't proved the dust. But there is a huge, and I want to mention this here because this is an ongoing discussion, there is a huge discussion of what an exocomet is because we cannot prove the composition. So we turned into the solar system people and we said, okay, what is a comet in the solar system? What is the proper definition? They were like, absolutely no idea. So we're back to the starting point. Like this historical classic separation between comets and asteroids in the solar system does not necessarily translate to the Beta Pic system. We just know that they have bodies that evaporate. And because they evaporate, we say they have tail, they're comets. Very big simplification. So we can do population studies in Beta Pic. At this point, this is 2014, we had around 2,000 spectra of Beta Pic with, more than 2,000 spectra, 2,000 exocomets detected in Beta Pic. 3 years, right? And there is a very interesting Nature paper by Flavian Kiefer where he shows that you can actually separate the comets based on the depth of the absorptions and on the radial velocity of the absorptions. And you can find that there are two families with different radial velocities, with different absorption depths, and it's not in this plot, but also with different possibly eccentricity. So there are like two distinct families of comets with different orbits that are in this system. And there have been a lot of theoretical dynamical studies about like what's going on with these objects, like why are there so many? Like, is there something in the system disrupting the bodies and throw them inwards, probably upwards, but don't we don't see. But that's still ongoing because the system gets more and more complicated. Since the advent of exoplanets, a lot of photometric intensive missions have come up, like Kepler and TESS. Plato is going to come up soon, and that allowed for just serendipitous detections of exocomets in transit. Like this is the optically thick, it's not super thick, but it's optically thick component, so the dust in the tails. And this is also in Beta Pictoris. Beta Pictoris was until, last year, the only system where we had exocomets in spectroscopy, in the calcium line, and in photometry. And exocomets have this really distinct shape. This is actually also more complicated. They have many different shapes depending on the impact parameter. But they have this distinct shape where we see the starting of a transit, and this could look like any exoplanet transit when it starts. But when the egress starts, it's an exponential decay because the tail exponentially decays. Like you have more material close to the nucleus and less material in the outer zones. So this is one way we use to distinguish these transits from something else. And for example, these deepers or single transit stars where we only see one transit but we never see it come back, we cannot tell if it's a comet or not if it doesn't have this shape, even though it could be a comet. And also thanks to these intensive missions, particularly to TESS, and the Cavalier de Setans, a couple of years ago, got a paper in Nature Astronomy where they distinguished, where they studied the sizes of the exocomets based on the depth of the transit and on the length of the transit. And so I've argued with him that this is a terrible fit, and he keeps saying like it's an amazing fit. And well, there's a little bit of both, right? Like you ask a statistics person, he will say like, okay, this line does not go through the points. But if you ask an economic person, it's like you're actually being able to tell something about the size distribution of the comets in Beta Pictoris. And what we are telling is that the size distribution of Beta Pictoris, of the comets in Beta Pictoris, is similar, or it's in the ballpark of a lot of small bodies in the solar system, which is great, but it also makes all the sense, right? Like we think the formation of these bodies would be very similar, either through aggregation or whatever, or collision and grinding. So yeah. And I'm just now getting started in the disk itself. So this is all about the comets. And the disk is incredibly fascinating on its own, and you'll see because that's the core of my talk. But one of the first things that we detected is that the disk looked kind of warped. This is a processed image. So before processing, like this distinction was not so clear. And everybody was saying like, oh, it's warped because there's probably a planet. And the location of the putative planet, when this was first discovered, this is before planets in Beta Pic were discovered, spoiler. The putative location of a planet that they argued for this warp, which was also discussed, it could be a secondary disk, was coincident with where you would put a big mass to disrupt the hyperbelt in the system and throw material inwards. So the same location where you would put a planet if you wanted lots of exocomets. So great. Everybody agrees. Thing is, this is a beautiful image from ACS, which is a camera on the Hubble Space Telescope. I think it's one of, I think it's the mission, or going to be the mission, because Hubble, it's going to cut down on budget. But we have images of the disk in a lot of wavelengths. This is a beautiful set from Daniel Apai's work. He has a great paper if you're ever working on disks or disk modeling or whatever. Go to that paper, even if it's not Beta Pic what you're interested in, because it's amazing. And he shows this beautiful normalized image of STIS, which is another instrument on Hubble. So the wavelength between ACS and STIS are actually kind of similar. And you can see here what I was talking about with the warp. Like this asymmetry that goes up in one side and down on the other side. This is an ACO, so this is also scattered light, but slightly longer wavelength. This is mid-infrared, what we have from mid-infrared from Beta Pic before James Webb. This image, well, there is also another instrument, but this was like the popular, like the famous one. It was also in a Nature paper by Charlie Telescope. And this image already shows that there is an asymmetry in the disk. Like you have the brightness in the inner region, where everybody thought like, okay, that's the star. We'll talk more about that later. And then there is an asymmetry here. ALMA shows an even bigger asymmetry. This is, we're still growing on wavelength. And a very flat disk, like we cannot kind of see the warp here, but we do see this. And that clump that we see in millimetric observations kind of is consistent with allocation of a lot of CO gas. Remember that thing of like, every disk don't have gas? Well, it's complicated. They do. We do think this gas is of secondary origin. So it's not from the postplanetary phase, but it's being released when collisions happen and within the dynamical activity of the systemic evaporation of these exocomets maybe. And it has a clump here. And we like don't really know why. And this was published in 2014, so only a year before this, by Bill Dent, also in a Nature paper, out of Nature from them. And they claim this was probably not a collision because the photo dissociation age of the CO was really quick. So it would have to be a collision within like less than 100 years, which was really unlikely. Blah, blah, blah. Everybody thought that collisions in the disks were like really unlikely. Spoiler. Yeah, so there is another particular thing about the ALMA data. It's not only the gas clump, but also that the gas disk seems to be slightly inclined with respect to the main disk, which kind of seems consistent with that secondary disk, posterior secondary disk that was kind of seen ACS. Going back to mid-infrared, not only we would see this asymmetry that we see on the southwest side, but further analysis and further reductions of this data showed that there is a bunch of clumps. So the disk is not really smooth. And again, we've seen this disk edge on. It's not based on like the stars up here. The star is like here in the middle, and we're only seeing one side. So this is might be radially, but it's definitely not asymmetrically smooth. And we don't really know why. But we know that there are some stuff in the disk that might be causing asymmetries. So there is one giant planet detected in 2008 by Marie-Lagrange. The paper is from 2009, but the press release was from 2008. And that planet was consistent with the location of that potential planet that would be creating a secondary disk and that would be throwing the exocomets inside. So, again, everything agrees with what we were seeing. So great, we have a planet, we have exocomets, we have a disk, we have a secondary disk, we have gas in calcium, we have gas in CO, we have inclined CO gas, we have clumps. Are you keeping up? It's a lot. Yeah, so the planet seems to be also misaligned with the main disk by just a few degrees, kind of like the secondary disk and the gas disk. So there is definitely something going on outside of the main plane of the disk. And then another planet was found. Beta Pic C was actually detected, again by Marie-Lagrange, but from radial velocity. To my knowledge, correct me if I'm wrong, there's plenty of expert people here, I guess. Beta Pic was the first system where two planets were discovered using different techniques, one imaging and one radial velocity. And if you remember, Beta Pictoris is an A-type star. What happens with A-type stars? It's really hard to find planets. It's really hard to look for transits. And it's really hard to look for radial velocities because all the lines are really rotationally broadened, and then they don't have that many lines because they're kind of hot. But also remember what I told you that we had like 2,000 exocomets in Beta Pic. That's because we had thousands and thousands of spectra of Beta Pic. And they kept taking more and more and more. They got to a point, they had so many spectra of Beta Pic that they were able to actually put together a radial velocity analysis and find a planet interior to Beta Pic B. So, can these planets be affecting the inner disk? Because now we got to a point where we have one planet that kind of fitted everything that we had hypothesized. Fitted the secondary disk, fitted the maybe kind of the clumps, the exocomets, but now you put another planet. Like, what the heck is going to happen now? So that just complicated a lot more the story. And there is a very nice paper that I forgot to cite here from Isabel, who is a theoretician that has done a lot of dynamical studies of Beta Pic, where he tries to put together a story with Beta Pic C in the mix, and seems to kind of work out, but then this doesn't really work, which kind of goes against what we think planets do in disks. So maybe the planets in Beta Pic are not clear in the disk. And this is still ongoing. So I will not give you an answer for this. Okay, so that was a very long introduction. But we're getting to it. I'm gonna focus the rest of the talk on James Webb data, because that's what I want to do in Baltimore. I want to work on Beta Pic in preparation and for the James Webb data that were taken as part of one of the guaranteed time programs, the GTO. And this is what you will see if you go to MAST, to the Space Telescope archive, and you go look for these images. This is in mid-infrared. You remember the images in mid-infrared that only had like a blob and then like some asymmetry to one of the sides? Well, we have a coronagraph now. We actually have two different coronagraphs. You'll see. And that coronagraph is allowing us to see the disk. And it is kind of symmetrical, so it's not really what we would expect from the other images we saw. But then, by looking at this, and I remember this was very close to Christmas, so we were like, oh, Christmas present. We started to see some weird stuff. Like, what is going on here? Like, are these artifacts? And like, of course, all the people that were instrument experts were like, yeah, artifacts. Like, this is going to go away with the reduction. Well, we have some, actually. You can see here the coronagraph bar. This is the physical bar that actually holds the coronagraphic mask, which is just a little piece of metal. And then some artifacts from the PSR. But what about all of this? Oh, sorry, yeah, I forgot I had this here. This is the people that helped me with the analysis. James Cameron is actually the second author in my paper, and Kellen Lawson is the third, I think. They're awesome. They did really great work, not only with this, but also with all the space telescope, early release science data that we have. Yeah, so after we did all the analysis, thanks to Jens and Kellen, with their fantastic, miraculous software, we got to this, and here is again the disk. It's not that asymmetrical. We have the coronagraph, of course. That's unavoidable. It's a physical thing. We're not going to get rid of it. We kind of see maybe a wall, like maybe it has that shape. Okay, but what is going on here? Like, what is all this? Because it's not here, it's not here, and it's not here. So then Kellen Lawson again worked his magic and the convolution of the data, which basically means just like subtracting the PSF from all the data. And then we started to see some really weird stuff. Of course, the people who were like experts on the instruments were still like, nah, that's just instrumental stuff, artifacts. That's obviously not astrophysical. Okay, fine, not astrophysical. But we have two roles because we wanted to avoid as much as possible background stuff, instrumental effects, PSF effects, and then we wanted to do self-subtraction in case we wanted to look for planets. So we took two roles. That means we took one image, we rotated the telescope a little bit, and we took another image. Okay. What happens if we put the two roles together? Roll one, roll two. And we combine them. None of these goes away. And what is this? So we started seeing some weird stuff, and this was it's an instrumental effect. Like, that is gone. Like, it's obviously astrophysical. Okay, it's a background stuff. What kind of background thing? It took us a lot of convincing that there is nothing instrumental about this, that there is nothing in the background that could look like this or have its PSF, or sorry, it's PSF, it's spectral distribution, and I'll talk about that. But this is something related to the disk. Okay, at this point we have, repeat with me, the disk, the secondary disk, the exocomets, two planets, clumps, gas, gas in the optical, gas clumps. And now we're adding this thing. It's like, stop it, please. But no, of course, we don't want this. So we found this in both data sets of the MIRI images. MIRI, it's the mid-infrared instrument in James Webb. We also have mid-infrared images, but I'll get to that. And we have them with the two different coronagraphs. So at this point, it was like, okay, this is not, we're not hallucinating this is there. But this is also there. And that's weird as well. And these images that you see, these pictures that you see, that a bright green and a dark up and stuff, this is because of this coronagraph. Okay, this is a different type of coronagraph than this one. That's why it looks so weird. And the main goal of this was actually just going really close to stuff. But the PSF is so complicated that the inner working on it's not that much greater. I mean, it's better than this, but it's not that much better. You see, we have artifacts up to like here. But yeah, so it looks great. We have beautiful images. We have really weird stuff that we don't understand. And so we started to work on that, and we started to work on the main features of what we characterize, what we said were the main features. One is this one, and one is this one. I don't know if you can see there, like there is a small, like thing in there. We call it the fork. Yeah. And this one we call the cat stay. I was in favor of calling it the hockey stick, but somebody said cat stay. And you know, astronomers and their pets. We have to have it. So yeah, so what's going on with the cat stay? Like, what's happening there? And we did, well, this is a beautiful image that was done by me, Marshall, and the Space Telescope graphics team, which is amazing. They're really good, and they're super, super helpful. When we put together both images that I just showed you, well, maybe without the cat, the 15 micron one and the 23 micron one, so they're like kind of separate wavelengths, but both in the mid-infrared. We put them together. The light one, the bluish one, it's the 15 micron, and the reddish one is the 23 micron. So we see here, the features that we see here, well, one is the really cute cat's tail, and the other one, we actually think it's a standard secondary disk, so we think this comes from the warp. So the warp is kind of here. Well, it's actually in this inner region that is not a coronagraph. But this warp that they call the secondary disk in 2006 seems to extend quite a lot, quite more than we thought. But just in the mid-infrared, we cannot see this in the optical or the near-infrared. And the cat's tail we definitely had no clue about, even though we have mid-infrared data from before. But yeah, this is how the system looks. And if you pay attention and you're kind of careful about it, you can see that there is also some color differences between what we see in the 50 micron and the 23 micron. Like it seems to light up at different places. So that means probably different compositions. Yeah. So what we think is happening in the cat's tail? Okay, so we never say a collision in the paper. We talk about collisions, but we never say, okay, this is definitely a collision because we don't know. But if you were to have a collision in a system like Beta Pictoris, or a dust production event, as we like to refer to it, you would have a point where you have your collision, your dust production event, and what would happen to the dust that is produced in that event differs a lot depending on the type of dust. There is this beta parameter, I forgot, no, I thought I had the definition here, but I don't. This beta parameter is defined as the ratio between how the gravity affects a particle and how the radiation affects a particle. So if the radiation affects more than the gravity, the particle is going to be expelled. When we're here. We're here in a hyperbola region if the ratio between the gravity and the radiative force is not exactly 1, but it's like kind of large. And if the gravity is definitely affecting more, then you have ellipses and you have Keplerian motion, essentially. So what happens in this dust production event? We're actually producing a lot of dust with different betas, with different effects that the radiation has on dust. So a lot of it is just going to continue to orbit the star in Keplerian orbit, and some of it is just going to be expelled of the system. And we actually think this is a dust production event, but it's not a single one. It's not just a one-time thing. We actually think it's a sporadic thing. So if that collision point or dust production point, this is happening quite a bunch. And this is producing not only the cat's tail, but a lot of other features that we are seeing in the image. If I go back, maybe it's easier to see. So all of these features are old cat's tails. That's what we think is happening. And all of this is coming from somewhere around here, which is kind of close-ish to some of the clumps that we see in the middle. Okay. Yeah. So based on the colors, we were actually able to say some things about what kind of dust we have. You see here the difference between bound and unbound. So here we have different compositions, different amounts of vacuum. So vacuum means it's porous, so it has like little holes in it, but yeah, there's nothing. Or if it's completely solid, like very high density. So for different compositions and different vacuum levels, we can have different betas that I was talking about. So what actually fits into having like really large betas and small betas? So it could be any of these, right? But then when we move to looking at the wavelength and how the spectra of those features would look like, it's the same colors for both sides. It seems that there is a slight preference for being bright at the wavelengths that we are observing of organics and vacuum. So we have organic material. And this came at the time when Osiris effects came back. So we were just retrieving organic material that has like a very similar spectral energy distribution from a real asteroid in the solar system. So it is possible that the cat's tail is composed of something similar to the Ryugu asteroid. Yeah, and we also played with the option that it was 100% organic or 0% vacuum, but that seems more unlikely based on the range of betas that we are having. So the difference between how the radiation and the gravity forces affect the dust, and we are ultimately vouching for the organics, but we are going to observe this. We're going to observe Beta Pic again this cycle with James Webb. And this time we're taking a spectra, we're just not taking images. So we'll know. And we're not only taking spectra, we're taking spectra specifically of the cat's tail. So we'll know. Oh yeah, I had the Beta Pic. Yeah, so this is a movie that also Space Telescope graphics team made. I think it's really cute, and you can see the collision point there, just happened, and how the cat's tail develops. This is the main disk, the orange one, the one that you would see in 23 microns, the red one in the picture. And this is the secondary disk that we would see in blue with the 15 micron. And this is kind of what the system looks like. So we have a lot of emission in 15 microns from the cat's tail and the secondary disk, but the main disk, it's brighter in the 23. And this is kind of what we think happened. If the dust just like are expelled, and this is actually an optical effect. It's not that the dust is coming up this way, it's actually going back. You want to play again? It's online, way. But yeah, there's the collision point or the dust production event. The dust leaves the system because of the radiative torque, the radiation pressure. And it looks like that. And it's just an optical effect based on the geometry of the system. Which also took us a while because it's like, why did you curve? Why did you change the slope? But yeah. We came up with this, and I think we're really happy with it. Okay, so I think I explained more or less all of these things, but there is still a lot of stuff we can talk about the disk. For example, the location of the clamp, of the CO clamp seen with them. So it's this clamp co-located with whatever is the collision point. We actually think the collision point happened, the collision point that created this cat's tail, happened like 150 years ago, which is more or less the time scale that they were defending for a collision to create that gas clamp. And they were saying like, yeah, there's no way we're going to have a collision like 150 years ago, it would be so lucky. Well, it kind of looks like we got lucky. And that's why we have the CO gas there, and why we have the beautiful cat's tail. Yeah, and more James Webb data, but this is not for cat's tail, not on my specific work, but I'm also part of this paper, so if you have questions, I guess I can answer. But this is a work by a PhD student that is extremely bright in the Johns Hopkins University, Keinan-Worthen, and he was in charge of analyzing the MRS, so the medium resolution instrument on James Webb, the MIRI, medium resolution instrument that has integral field spectroscopy. So you actually have a bunch of images and you can construct a spectra, but especially to solid spectra. And what they wanted to see is what was the composition of the dust in Beta Pic, but like close-ish to the star, because the field of view of the MRS is much smaller than the field of view of the imager of MIRI. So they did this kind of experiment, which I thought was really cool. This is the aperture of James Webb, so smaller than this, you're not considered that your result. This is PSR. And this is where they extracted the spectra, like not specifically here, but like in the image, it's more or less this size. And they compared to what Spitzer, which was a telescope that is no longer functioning since not so many years ago, what Spitzer could do, because Spitzer also had data of Beta Pic, of course. And they found this incredibly cool result. That is like, this is the spectra from 2004, and this is the spectra from 2023. 20 years, 19 years have passed between one spectrum and the other, and there are incredible changes. It's the same star. Again, one is with James Webb with this aperture. It's not that they're using this small aperture. They're using the big aperture to directly compare the same region. So this is the James Webb data with this aperture, and then the Spitzer data with a similar aperture. And they find this. So what happened here? We have features that are disappearing. These are silicate features. These are dust features. I think it's Forsterite, and I don't remember. You can go to the paper if you want to know specifically. They also do a beautiful modeling of the spectra. But yeah, like some things are gone, and then this flux is much lower. So what happened here was actually a collision. When this data was taken in 2004, there had been a recent collision that cleared up in the next 20 years. Is this the same collision as a cat's tail? No. Why not? Because it cleared up in 20 years, and the cat's tail has not cleared up in 20 years. So this is much more likely to be a different collision that happened in the inner regions of the system. Here, we are inside of the coronagraph from the images before. We're not getting to this part of the disk with the other images. And yeah, vice versa, we're also not seeing the inner parts with the coronagraphic images. So yeah, it's not only proof that there has been a collision in the disk, we now have proof that there are multiple collisions. We're talking in the past 150 years, we at least have proof for 2 of them. So we used to think that the disks were dynamically active in the sense that they were producing dust and maybe some gas, but not that there were this type of giant collisions that can effectively alter the composition and the morphology of the disk. So this was like a huge advantage in the field that I'm really happy I was part of. And yeah, we also checked a couple more things from the disk. For example, the clumps, if you remember, that we had seen from the ground. And it's kind of tricky to say if they're there, but they seem to be. So this definitely needs a better specific analysis for that. Like there were so many things in the disk that we cannot tackle everything in one paper. If any of you feel energetic, okay. The data is public. And another weird stuff that we found in the disk, and this is also in this paper, is that there is argon 2 in the disk. And we have not explained this yet either. We don't understand what was happening here. Like one of the hypotheses is like, okay, this argon is unresolved, and it's somehow in the chromosphere of the star. I don't know, chromospheres are weird, complicated, maybe, but the argon is extended. It's like, well, what is going on? And it's not only extended, like you see this blob here, there is something there. This is not argon, this is just like the argon lines on one of the images in a different wavelength range. You can see the disk. But I'll get to that point. So we don't really know what's going on there. We found it, we cannot really explain it very well. It doesn't make sense to have a noble gas ionized in a disk that it's kind of chill, or we suppose like doesn't have a lot going on at really high temperature. Yeah, that little blob that we saw, that we see in this image, the little blob that we see here, this is MIRI data, remember MIRI MRS, the spectrograph. We also see in the NIRCam images. I told you we have NIRCam images, but we didn't focus that much on the disk, because the disk in NIRCam is like, what do we expect? It's a disk. It's a kind of normal disk, maybe has a little warp here, but we see something a bit more interesting, that it's Beta Pic B. So Beta Pic B is in this disk, here, 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 maybe more clearly. And we can detect it. We actually have like pretty nice detection curves. So we were able to nicely detect it. We cannot reach Beta Pic C. Beta Pic C is like much further in. So it would be around here, I think. But Beta Pic B, we can see. It would be, Beta Pic C is almost inside of the coronagraph, or inside the coronagraph. Yeah, so even having a disk, you see that the solid lines, this, well, this, yeah, I think I changed it. But I either changed the image or you don't remember. These are the detection limits with the disk. So the disk kind of like blocks a lot of detection abilities. But we still can see the planet there in all of the NIRCam images. You cannot trust me, but in the paper it's more clearly explained. In the paper by Jens. But we had like a kind of a pointing issue, so for a while we were also doubting it. This was actually Beta Pic. And just a cautious tale, we used Alpha Pic as a reference. It's the most typical star that we use as a reference for Beta Pic because it's close, it's Alpha Pic. It's brighter than Beta Pic, so it's really easy. We kind of think it's a binary, and that's why we were not able to find the center. Beta Pic has been used as Alpha Pic has been used as a reference star for 50 plus years, or 50 years. Nobody found anything like this until we got to the sensitivity of James Webb. So if anyone wants to investigate on the binarity of Alpha Pic, go ahead. Oh, no. Okay. I wanted to see you the spectrum, but I don't know what happened to this plot. Okay, sorry, not to Jens' paper, please. Because this is the spectra of the planet with the James Webb points. I promise I didn't do this, like there's a lot of stuff missing. But it shows the fit, and we have like two different kind of fits, but they are very similar. The only change is mostly the C2O ratio, which experienced people know it's really hard to actually tackle and to disentangle for planets. And again, we have the difficulty that we have the planet very embedded in the disk, so we have to subtract the disk, and that's really tricky. But yeah, it's already nice. Oh, okay, you can see this one. Yeah, so Caden has also in his paper in 2024 the same data that Jens published in his Camera 2024, which is this. Yeah, this. Okay. And this is the spectra from the MRS. So it kind of fits a very similar model than Jens had, if you had seen the plot before. But yeah, so it kind of further constrained a little bit the C2O ratio, but not great. So really the NIRCam photometry for Beta Pic B didn't say anything unexpected or anything like crazy new. That's nice to have it. Oh, here is it. Okay. Sorry. Okay, so I'm gonna stop here because I'm already 5 minutes past. And I nicely got to my summary. But yeah, my main takeaway is that Beta Pic is a complex, interesting system. Like if you remember all the things that I told you, like the disk, the secondary disk, the planets, the exocomets, I don't know, I'm not going to do it all again. But it's a very complex system. It's nice that it's so close because we can get a lot of data, really good data, really high quality data. And it really gives us an insight on how planetary systems are formed or how the earliest stages of planetary systems are. This is an A-type star, it's not a G-type star, so maybe there are some steps or like some processes that are different for stars like our sun. But overall, and we saw from the sizes of the small bodies, overall there are similarities. So it's really interesting to study these type of systems. We are still working on this, and I'm really, oh, no, I hit the wrong button. We're still looking into this, and I'm really interested to see what comes out of it. But I really want to know if exocomets are connected to collisions somehow. It's really tricky to say though, because the dynamical models that you would have to do for that are insane. We're talking an body simulation at least, and collision simulations, super complicated. But I would hope that if we manage to get some of the exocomet compositions, which we don't have, maybe we can tie it to some of the collision leftover material. But yeah, and then some other stuff that I showed you that I hope you remember, it's that the MIRI images from James Webb show the fork, so the secondary disk end and the cat tail on the other side. We have no new planets in NIRCam, I didn't say that, but it's telling you now we don't have any new planets. But we have kind of reasonable deep limits for a star with such bright disk. So that was really cool. The NIRCam photometry is like what we expected of Beta Pic B based on other ground-based efforts like NACO data and gravity data. And extracting the accurate planetary photometry from the disk is really hard. So most of the people that want to actually study the composition of disks, or sorry, the composition of planets, or study do models of the atmospheres of the planets, etc., are probably going to go to other planets and not these ones, because these ones are really, really tricky. And yeah, and we have at least one more program that is going to look into Beta Pic. It's an MRS program that is just going to focus on this side, here, where the cat's tail and the nebulosity is. So we'll hopefully know the composition of the cat's tail soon, if everything goes well. And that's it. Thank you very much.
Thank you very much, Isabel. Amazing results. So we have time for questions now.
Or online. Yeah, feel free to, yeah.
Regarding the exocomets of the beginning, how do you compute the size of the exocomet?
Yeah.
You showed a plot there of
Yeah.
10 kilometers. How do you compute that?
Yeah, so that's kind of tricky. So they use I recommend you to look at the paper, because I have to read it like a couple of times. But they use the transit, they see the full transit, and so they use the transit length to compute the distance, and then I think they use the depth. They model it because Alain Cavalier was the one who predicted these transits also in 1999. And he has models of how the curve looks for different types of comet, depending on from the impact parameter and stuff, and he uses the models to predict the sizes.
About the exocomets, what is the clear evidence that are exocomets and not other things in this?
Oh, none. None. We're happy to hear other hypotheses. But so it is tricky, right? Because we see very different things in spectroscopy and photometry. For years, when we saw them in spectroscopy, we were like, okay, when we see the dust counterpart of this, then we'll be sure, because they have the gas tail and the dust tail, just like comets do in the solar system. But then we found the dust tails, and they actually have sort of a different distribution. They don't seem to connect the spectroscopic features with the photometric features. A photometric feature can last for 3 days, when a spectroscopic feature might last for an hour. So it is kind of tricky to connect them, and it's kind of tricky to fail-proof them, to say like, okay, this is definitely a comet. But the thing is, we have not found any other hypothesis that matches what we see. Like, we don't think it's anything from the star, because it would be rotationally broadened. We don't think it's anything from the interstellar medium, because it would show in like close-ish stars to Beta Pic and other Beta Pic moving group stars, maybe. We cannot find another hypothesis that suits everything that we see. And that one seems to work with everything.
And at some moment there are some simultaneous observation in spectroscopy and photometry?
No. Yeah, that's one of the things we always discuss. And I say we because like we already had 2 exocomets meeting with like the international community. Yes, there is an international community of this. And we can't find the best way to produce this type of observations, because when a transit starts in photometry, again, it can last for days, it can last for half a day, but it's not processed until we see the full light curve. So we don't know, we cannot see a transit in photometry starting and then trigger the observation spectroscopy. Like with the current instrumentation, we cannot do that. And we cannot do otherwise, because if we are observing the transit in a spectroscopy, and you would have to trigger the photometry ones, you cannot go to space and say like, hey, Tess, move to Beta Pic now. So it is really complicated, and it's really, really hard to do this from the ground, because we're talking really small transits, like the parts per million. Insignificant, they're really, really small.
This is a very bright star, no?
It is a really bright star.
Could you get away with a CubeSat?
You could get away with a CubeSat. Yes, brilliant idea. There was a CubeSat. They sent in a CubeSat that was called PicSat, and that was the idea. They were just going to do that. It failed. It launched, it got in orbit, stopped responding.
It's another.
Tell France. Everyone wants to do this. No, but yeah, and then at some point the CubeSat woke up miraculously and they were like, oh, let's do something with it. But then one of the instruments was not working because it was 3 years or 4 years after launch and whatever happened. So yeah, somebody thought about it, it just didn't work. But I agree, it's the way to go, which is, I don't know. Anybody have money?
And for the observation,
I think Armando has a question.
No.
Okay.
I will.
Okay.
from the observation, you deduce what distance are from the star. So it's, these comets, suppose comets, are just in the disk or are in the green region of the disk when the planets are.
No, so depends. The exocomets we see in spectroscopy are really close to a star. I actually think there are two different populations when we see them in spectroscopy and photometry. So the comets we see in spectroscopy, we see them mostly in refractory elements. So I talked about calcium, but there is actually ultraviolet observations that also see them in magnesium, in silicon, in a lot of different, in carbon. But in order to evaporate those materials, you need to be really hot. We're talking 1500 Kelvin or so. In order to get to that temperature, you need to be really close to the star. So the distance to the star is probably just a few stellar radii. But when we're talking the photometric ones, that's the dust. And the dust doesn't evaporate or sublimate. That is released when you evaporate or sublimate the volatiles, the water, the CO, the CO2, whatever is in the comet. So that can be much further out. So the dynamical models, so far, they tell us that both the transiting spectroscopic ones are inwards of both planets. So there is actually material that is inwards of both planets. But it is hard to know. Yeah, hard to trace the exact distance. We don't have the eccentricity. There is a lot of parameters we don't really have from the comets, so it's tricky.
Mm-hmm.
Well, she already replied to my question. The other one is about ARM observations of other molecules that are typical for comets here in the solar system. But you already said that it's too hot, so maybe this material is not.
Yeah, so molecules is complicated in these disks because we barely have any gas. The gas that we have is being released in these evaporations, in collisions, so it's very residual amounts. It's not like a protoplanetary disk. So in order to see that gas, you need to go to very high sensitivities, which ARMA has, but we have not found anything that is not CO in the Beta Pic. We have found carbon, but not molecular carbon. Carbon-1, atomic carbon. So we don't really know what's going on. We actually had, I had a program, and there was another program, Christine Chen, by the way, the same person who did these MRS images, to use NIRSpec and go to the near infrared and try to look for molecules there, specifically water. Because water is everywhere. What is it in the disks? And it has never been found in the disks. And we don't see anything. We see argon, but we don't see water. So, yeah.
Armando?
Thank you, Isabel. It's really impressive. There's one question. The fact that you have this morphology is because you used two names for that. You said production or
the dust production.
You say the dust production, and you say also collision. So I don't know if you
Yeah.
say or you want to cover your back the same.
Oh yeah, I want to cover my back. Yeah.
But the other thing is, if this production event, you seem to also say that it's a collision. So it's some kind of material that is falling to the disk. Because it has to, it cannot be in the disk forever because you see it outside the disk, right?
Yeah,
So it's coming from above, and then some part is coming away because it has the dust that produces it.
So
it's more subject to
so
pressure. Or?
nothing is coming into the disk. Things are going out of the disk. What is causing the dust production event or the collision? Let's say, Maybe I'll show you here. And this is something I actually forgot to mention, and I should have. We think the secondary disk is. So we have a main plane of the disk, where we have most of the material, and then we have a secondary disk. Well, we don't think the secondary disk is a product of this collision. We actually think the secondary disk is a product of perturbations from the planet B. So the planet B is moving material, because the planet B is also like not in the same plane as the main disk. So the planet B is moving material with it and is generating the secondary disk. What happens when you have two disks that are like this? There are some point, if the density of material is high enough, they're gonna find each other and they're gonna collide. So the presence of the two disks is generating a collision where you are, what is the beta? Okay, this one. You're generating a collision where some of the dust is being released from the system, it's being blown away by the radiation pressure, and then the rest is staying in the disk. It's in the secondary disk. It's rotating in the secondary disk.
So the cat's tail is always in the secondary disk. It doesn't go above or below.
It goes in the plane of the secondary disk. Yes, correct. It's
And
like,
always there. So it's just that the
yeah, it's not like it's going like this and you have the disk here. It goes like this. It goes with the secondary disk. It's only like a 5-degree tilt. This is an optical effect, but this it's on the same plane as this. So here, I can't do it.
and it's not perfectly etched on.
No, because neither the main disk or the secondary disk are perfectly etched on. The main disk is like 80 something degrees, and the secondary disk is 5 degrees with that, so like 80. So yeah, but we think the cat's tail it's more or less in the same plane as the secondary disk. Yeah, that's a good question. We also have to explain that, because how do you needed to have, if you actually have the cat's tail going up like this from the disk, you would need to have something that was already excited to these angles. And that was really hard to explain. But if we only have to explain 5 degrees, we already have it because we have the secondary disk. Yeah. So this is an optical effect. This is actually the same inclination as this. Just like moving backwards and looking weird.
Right.
And what is the lifetime for this cat tail?
Oh, we actually estimated that, and I forgot. Hundreds of years in the scale of hundreds.
It's, you cannot expect to see variation.
Yeah. We actually, for the cycle 3 proposal that we have, the one that is going to be observed hopefully in a couple of months, we expect to see 2 pixels variation in the position or something crazy like that. And I remember doing the numbers, and the PI Marshall, who was my supervisor, was like, "Oh, 2 pixels, plenty." Sure. So everything for these people that are really, really experts of imaging data, everything that is not subpixel, it's more than enough. Sure. So yeah, we expect to see that. If everything, if our hypotheses are correct, we will see it move a little.
Okay.
Yeah.
Any other questions?
Isn't there any questions from the women in the room?
Well, I have curiosity. With your future NRS data, will you be able to derive a kinematic map of this system?
No, because there is no gas. You can derive a kinematic map if you have the gas. I mean, maybe we have gas.
If you have argon too, as you show.
Yeah, but the argon, I don't
just close to the.
The argon is in the inner region. Yeah, so it's just here, which would be, I don't know, here. So we will not see it in this area here.
What kind of emission line do you expect to find?
So it's going to be continuum emission. Because that's what we expect. We expect to only see the dust. I don't know, we're up for any surprises at this point. But in theory, we are not going to see any dust. Oh, sorry, any gas. Yeah, so we thought of that, of course, and we don't see it in the ALMA data, which is like a very high sensitivity on gas that we know it's in the system, but we just don't see it, so it would be amazing. Yeah. Yeah.
So, any questions online? And if not, I think we can thank Isabel again.
summary after that.
Thank you everyone for joining us.
Thank you for coming.
Thank you.